So let's look at our first example here. Our first example says, analyze and sketch the graph of f of x equals negative x cubed plus 3x squared plus 9x minus 27. So the ultimate goal is, I want to tell you absolutely everything important about this function and sketch this function, again, without using technology. How do I do it? Well, to be able to do it, what I want to do is be able to analyze the function, its derivative, the second derivative, then put everything together, and then sketch a rough graph. So let's start off with the first three questions, analyzing the original function. If we analyze the original function, we can answer the domain, the x-intercepts, and the y-intercepts. Remember, domain is what numbers can you plug into the function. Well, if you note that this is a polynomial function, and polynomial functions are defined everywhere, so that means the domain of this graph is negative infinity to infinity. Why do we care about that? Because if you remember, for any polynomial function, the domain is also intervals of continuity. This graph is continuous from negative infinity to infinity as well. Okay, so let's look at the x-intercepts. How do you find x-intercepts? X-intercepts occur when y equals 0, or if it's written in function notation, all you have to do is set the function equal to 0 and solve. Well, this is a large cubic function. It might seem a little difficult to set equal to 0, so you might want to remember some of the old factoring techniques that you learned back in intermediate algebra. One of the factoring techniques is factoring by grouping, where you look at what do the first two terms have in common and what do the second two terms have in common. Let's give that a try now. Looking at the first two terms, it looks like they have an x squared, and anytime you can, actually factor out that negative x squared. So if I factored out a negative x squared from that, negative x cubed divided by negative x squared is x, and 3x squared divided by negative x squared would be a minus 3. Let's look at our second two terms, the 9x minus 27. Those have a 9 in common. 9x divided by 9 would leave a 3x, and minus 27 divided by 9 would leave us, 9x divided by 9 would leave us with an x, and negative 27 divided by 9 would give us a negative 3. So what are we saying? We're saying this is really the exact same thing as negative x squared times x minus 3 plus 9 times x minus 3 equals 0. We've factored by grouping. Now if you notice, looking at these factors, they both have an x minus 3 in common, so we could factor out the x minus 3. If we factor out the x minus 3 from both of these, seems like my first term would be a negative x squared would be left, and with the second term I'd have a plus 9. So by doing this, we've actually factored out what we needed to factor out. We have x minus 3, that quantity, times negative x squared plus 9, and that's equal to 0. Now we have the factors equal to 0, and by the multiplication of 0 principle, this equals 0 if and only if one of the factors equals 0. So I set the factors equal to 0 and I solve. Add 3 to both sides, I get x equals 3. That's one of my x-intercepts. Negative x squared equals 9. Negative x squared plus 9 equals 0. Add x squared to both sides, you'd have x squared equals 9. Take the square root of both sides, never forget plus or minus, and you'd have x equals plus or minus 3. So from these three values right here, 3, plus and minus 3, that gives me my x-intercepts. Remember, when you write x-intercepts, it's not an x value. An x-intercept is a point on the graph. And in particular, an x-intercept is when y equals 0 or the function equals 0. So that means our x-intercepts would be the points negative 3, 0, and 3, 0. The values that we found for x paired with y values of 0. Finding y-intercepts is nice and easy. To find a y-intercept, all you have to do is plug in x equals 0. So go to the original function, plug in 0 for x, you'd have negative 0 cubed plus 3 times 0 squared plus 9 times 0 minus 27. And that's going to give us our y-intercept. Our y-intercept in this case is negative 27. Now what I said was technically mathematically wrong. The y value of our intercept is negative 27, but remember this has to be written as an ordered pair. A y-intercept is when x equals 0, so because our y value is negative 27 and x equals 0, we have the ordered pair 0, negative 27. So why do we do this? Why do we analyze the original function? Well, when we go to graph it, now we know 3 specific points on the graph. I know the X-intercepts are negative 3, 0, and 3, 0, and I could also plot a Y-intercept of the point 0, negative 27. And then another thing that's going to help me is knowing that this graph is technically continuous everywhere. So I'm going to be able to analyze the derivative everywhere at this point and be able to use the first and second derivative tests as we always have. We've now analyzed the original function, so let's start messing with the derivative. If we want to find intervals of increasing, decreasing, and relative extrema, we need to find the derivative. So I'm going to just real quick write down the original function here. The original function was negative x cubed plus 3x squared plus 9x minus 27. What we need to do is analyze the derivative, so let's find the derivative and find its critical values. The derivative using the power rule would be negative 3x squared plus 6x plus 9. Derivative of negative 27 is 0, of course. We take this equation and define the critical values. We set it equal to 0 or undefined. Okay, well, this is never undefined because it's a polynomial function. And so now I need to solve this equal to 0. Well, what could I do? I could use the quadratic formula, or I could try to factor, or use any of the multiple techniques that I know. One thing that I do see is that everything's divisible by negative 3, so that's what I'm going to do to try to make my numbers smaller, to see if potentially I can factor this. So if I divide negative 3x squared by negative 3, I'd have x squared. 6x divided by negative 3 would be minus 2x. 9 divided by negative 3 would be minus 3, and that equals 0. Again, I want you to realize that this is our first derivative, but now I'm trying to solve the equation. But we are going to need that first derivative later on when we look for the second derivative. Okay, let's look at this quadratic now. Again, I could have used the quadratic formula, but I'm going to try factoring. I need two numbers that multiply to be negative 3 and add to be negative 2. Seems to me like I can easily find those as x minus 3 and x plus 1. Set that equal to 0. Let me just FOIL that out real quick. I'd have x squared plus x minus 3x, which gives me my minus 2x. Then I'd have minus 3, so it does look like that is factored properly. I set each one of those factors equal to 0 and solve. I end up with x equals 3. And on the second equation, I'd end up with x equals negative 1. Again, these points right here are called my critical values. Those are the points where the first derivative is set equal to 0. So the next step of the process was to create a number line. We're going to be looking at the derivative. We're going to plot those points on a number line. Here's the point negative 1. Here's the point 3. I know my derivative is 0 at both of those points. I need to break it into the intervals. The first interval would be negative infinity to negative 1. Second interval is negative 1 to 3. Third interval is 3 to infinity. And now I need to choose a test point. Again, I'm looking for increasing, decreasing. So I need to choose a test point and plug it into the first derivative. I'm going to plug it into the original first derivative. You've got to be really careful with this. If you plugged it into the factored one when we divided everything by negative 3, that's technically not the derivative. This does factor. We could have factored this, but I'm just going to plug it in right here, and I'm going to use my calculator. I'm going to use my trusty old test points. I'll use negative 10, 0, and 10. That's in the first, middle, and third interval. Make sure you pick points in those third intervals. And then plug this into your calculator and see what values you're getting. Again, you only care about positives and negatives. I'll do that now. Looks like on the first interval I'm getting a negative. When I plug in 0, it looks like I would get a positive. When I plugged in a 10, it looked like I got a negative. So I'm going to go to my sign chart, or that little number line. I'm going to say because that first test point was negative, that entire interval is negative. Second test point was positive, so the entire interval is positive. Third test point was negative, so that entire interval is negative. Again, I know whenever my derivative is negative and I look at that original function, it's decreasing. Anywhere it's positive, it's increasing. Again, negative would mean it's decreasing. At negative 1, because it goes from decreasing to increasing, I know that has to be a minimum. And at 3, because of the first derivative test, I go from increasing to decreasing, I know that has to be a maximum. Again, when I write maximums and minimums, I actually need ordered pairs. So the way you find the ordered pair again is by plugging the number into the original function. So I have to plug in negative 1 and I have to plug in 3 to the original function. The original function was negative. then it was x, the x value cubed, plus 3 times that x value squared, plus 9 times that x value, minus 27. I do the exact same thing with 3. I plug those numbers into my calculator and see what I get. When I plugged in -1, I got the number -32. When I plugged in the number 3, I got the number 0. We actually knew that point, but that's good. So what do I know then? I know that the point -1, -32 has to be a minimum. And I also know the point 3, 0 has to be a local or relative maximum. So let's put all this together. When was this function increasing? It was increasing when the derivative was positive, which was on the interval -1 to 3. When was this function decreasing? It was decreasing when the derivative was negative. That had happened in 2 separate places. That is on the intervals -infinity to -1, and also 3 to infinity. We scroll down and we look, where was our maximum point here? Our relative maximum occurred at the point 3, 0. And our minimum occurred at the point -1, -32. Again, this is going to give me 2 points that I could plot on the actual graph. And it also is going to give me some good information to help determine the shape of the graph during the intervals. So we will use all of this information very shortly on the next page.